Good evening, and thank you very much for coming. Please join me for a journey which we find fascinating and which, in fact, from our point of view here at Stanford has just begun. If you could have read the New York Times on July 16, 1907, you would have found on the front page the headlines of a big literary find in Constantinople. The Danish scholar Johann Ludwig Heiberg had discovered a series of ancient writings inside a 12th century prayer book. And it is this book with which our journey today is concerned about. But let us go back another 2,500 years. What might look to you like the Sierra foothills on an early summer day is in fact the location where on September 11, 490 BC, the fate of Western civilization was hanging on a very thin thread. A huge Persian army led by King Darius had landed on the Greek shore in the Bay of Marathon. Estimates about the size ranged from 20 to 60,000 men strong. After several days of discussion and consultation, the Athenians decided to go to face the enemy, and they sent into the Valley of Marathon an army of 10,000 Athenians with the help of 1,000 Plataeans. Being about 1,600 yards from the front line of the Persian archers, the Athenians did the usual thing. They organized their troops into a large phalanx where they protected themselves basically like a turtle with all their shields and started to march. It took about 10 minutes. When they reached the range of the Persian archers to about 200 yards. At that point, something happened which hadn't happened in the history of warfare before. Rather than continuing their march and being exposed to the hail of arrows, they started to rush in a almost sprint into the front and did such a surprise attack. Avoiding the arrows, they got immediately into an infight, and it took only part of a day before the stronger equipped Greek Athenian soldiers had beaten the Persians. At the end of the battle, 6,400 Persian soldiers were killed and only 192 Greek fighters, upon which the Persians decided to flee. One of the fighters, Phidippides, after fighting all day, had to run 26 miles to Athens to deliver the message of victory, upon which he dropped dead. There might be some people amongst you who regret that Athens is actually that far away from the Bay of Marathon. The Battle of Marathon was the first victory of a new form of government. It was the first victory of the Occident over the Orient, and it is considered as one of the most important events marking the birth of Western culture and the beginning of the age of classics. They are no man's slave and no man's subject, was said about the Athenians. They are proud, the Athenians, the victorious democrats. Self-confident and ambitious, approaching arrogance. Sounds familiar. They have a mentality that leads them to enormous accomplishments in politics, arts, philosophy, and architecture. There were the great Greek philosophers. Socrates, born only 20 years after the Battle of Marathon, the questioner. His most famous phrase, "All I know is I know nothing." His student, Plato, the idealist, who wrote among many important works, The Republic. And his student, Aristotle, the taxonomist, who was, amongst many other accomplishments, the educator of a 13-year-old boy who turned out later to be known as Alexander the Great. And there were the mathematicians, Euclid of Alexandria. His concept of space, in fact of three-dimensional space, has survived 2200 years until a former patent clerk of the name Albert Einstein discovered that in fact space is not three-dimensional. There is a fourth dimension, time, multiplied with a constant, the speed of light, which is perpendicular to the three dimensions. He later also realized that this four-dimensional space-time is actually not straight, but it's curved under the influence of gravity. And this resulted in the general theory of relativity, still valid and confirmed many times. It will be seen how long Einstein's concept of our universe will hold. There are strong doubts it will survive 2200 years. Certainly string theorists don't hope so. And then there was the greatest of them all, Archimedes of Syracuse. Born in the city-state of Syracuse on the island of Sicily, and in an unfortunate event killed at the age of 74 by a Roman soldier who didn't follow his orders. Archimedes was famous at the time. The Romans had ordered to capture him alive. He was such a valuable person. But supposedly, deep into thoughts about mathematical problems, he didn't follow the orders and was killed. Archimedes, as a student, was sent to Alexandria to learn the teachings of Euclid and actually also of Aristotle. Amongst his many accomplishments in mathematics, engineering, warfare, and science is the famous pulley, a means with which you can pull a weight many times heavier than yourself. The famous Archimedes screw, a pumping system still used in many places around the world, with which you can pump water from a lower level to a higher level. During the siege of Syracuse, Archimedes employed a combination of hooks and levers, and the Roman battleships which were anchored at the quay, these hooks were brought underneath and they were shaken. Some of them tipped over, and the soldiers were scared to death. The most famous story about Archimedes, however, is his Eureka moment. The king of Syracuse had asked the goldsmith to make him a wreath, and he had suspected that the goldsmith had mixed some lesser noble metal within the gold, and which is also lighter. He asked Archimedes to help him solve the problem. At the time of Archimedes, it was relatively easy to weigh an object. However, in order to determine whether it's gold or not, you needed to know the density. And for that, you need to know not only the weight, but also the volume. How could you ever determine the volume of such a complex object like a wreath? Archimedes, supposedly taking a bath, all of a sudden got a great idea. The water in his bathtub, which he moved away with his body, had exactly the same volume of his own body, no matter how complicated and irregular his own body was. And by knowing that, you had a way to measure the volume. Now all you had to do, measure the weight. So a possible experiment how to do this is you put a balance beam, you put the amount of gold equal to the amount in the wreath, and then you dip them both into the water. If the wreath has a larger volume, it'll get a stronger lift, and the balance will get out of balance. In that matter, the king actually realized that the goldsmith wasn't a dishonest man. He had put some lesser noble metal into the wreath. Archimedes also invented the law of the lever. And everyone who has played with their children on a teeter-totter knows how valuable that is. It tells you that the mass A and times the distance A of the center on a balance equals the distance B times the mass B are on the same balance in order to stay in equilibrium. And I will show you now, in a short version, how Archimedes did the proof of this important concept. I'll show it in reverse, how he did it, but I think it's better for the illustrations. Imagine you have two objects of equal mass at an equal distance. Your balance beam will be perfectly straight. Now, of course, you could replace them by four objects similarly spaced, or without disturbing anything, you could place these four objects close to the middle and put them in one large, as long as they're always at the exact same distance from the balance. Now imagine you take 16, 8 on either side. You take 4 of them and replace them with one which is 4 times as heavy. You will not bring the balance, you will not disturb the balance. You take the other ones and do the same thing. In this case, it's 12, and you replace them by 12. All you have to do now is remind yourself at which place these objects were, and you know that, because this object is exactly at this location, and the object of 12 is exactly in between the 6 on either side. You can measure that, and you have the law of the lever. This law has dramatic consequences, of course, because it tells you that in principle, you could lift something extremely heavy as long as your beam is long enough. And that led to the famous saying, "Give me where to stand and I will move the earth," which is, of course, not to be taken literally. But Archimedes was well aware of the power of the law of the lever. In fact, Archimedes was so famous at its time that as his fame grew, his challenges grew as well. At one point, the king of Syracuse asked him, at one point, Archimedes took a combination of levers and pulleys and pulled a ship all by himself on land. The king was so impressed and said, "From now on, we have to believe what Archimedes is saying." Scientists sometimes hope that the reigning bodies today would have the same respect for them. Archimedes' one of his most famous mathematical accomplishments was the determination of the number pi. It is compared to the mathematical invention of the wheel. Pi is the ratio of the diameter and the circumference of a circle. And Archimedes used the following estimate. He knew how to calculate the length of the 3 sides of a triangle. And he said, well, I know that the triangle that length has to be shorter than the sphere because all of it is inside the sphere. Then he said, why not divide these 3 sides and create an hexagon? And then he knew also how to calculate the side of each hexagon. And if you add up all the 6 sides, you will still get a number which is smaller than the circle because it's still inside the circle. However, it is already much closer. He continued that through 12 sides, 24, 48, until 96. At that point, he had a very good lower limit of the circumference. And then he said, let's do the same thing from the outside. So he started from the outside and also went to 96. By those 2 methods, he had an upper limit and a lower limit, and he got the value to a precision of 3.14, a value which is still used by many who work in the construction as good enough. Archimedes had a friend, Eratosthenes. He was 11 years younger, and Archimedes was kind of a mentor for him. Eratosthenes is famous because he was the first person to measure the size of the earth. How did he do it? The city of Aswan lies directly on the Tropic of Cancer. That means on June 21st, at noon, there is no shadow. The sun is directly overhead. And here I'll show you the situation of the Earth. This is the equator, this is the north-south, and the Tropic of Cancer would be this line, basically. This is the rays from the sun at noon. Eratosthenes, who came from Alexandria, also knew that at the same time, on the same day, there was, in fact, a small shadow, and he could measure it. It was about a 7-degree angle of the sun. He knew the distance between the two cities from the caravan travelings. It was about 5,000 stadia, and one stadium is about 185 meters. All he had to do now, take that distance, multiply it by 360, divided by 7, and he got the estimate of the Earth. His number was falling, and it's partly to the uncertainty of its angle, partly to the uncertainty of what exactly one stadium is. It is believed to have fallen with between 39 and 46,000 kilometers, and the exact value is 40,000 kilometers. It's a remarkable achievement for that time. Before the war, we know that Archimedes wrote a letter to his friend, Eratosthenes. Greetings. Since I know you are diligent and excellent teacher of philosophy and greatly interested in any mathematical investigation that may come your way, I thought it might be appropriate to write down and set forth for you a certain special method. He later continued, I presume there will be some among the present as well as future generations who by means of the method explained will be enabled to find other theorems which have not yet fallen to our share. Only through a miracle, if you want, or through a series of fortunate circumstances did this letter actually survive until today. And in fact, the method which Archimedes describes in here is of greatest significance, which I will show you in a second. In Archimedes' time, his work was written on papyrus. It was then copied also on papyrus scroll. Here you have a drawing of Archimedes writing on papyrus scroll. In the 4th century, the scribes changed their method. They started to use parchment made out of mostly goat and sheep skin, and they used an iron gall ink for their writings. And the Archimedes texts, or the Archimedes letter in this case, was then written on a parchment. It is believed that the last time these texts were written was in the 10th century, in the second half of the 10th century, probably in Constantinople. However, in the 12th century, the Fourth Crusade sacked Constantinople, and his parchment book was taken apart, and in a common practice at the time, reused for other, mostly religious writings. We are now in the deep part of the Dark Ages. There was no interest in mathematics, and it was very hard to get by parchment. So this was an early method of recycling. And here's how a palimpsest standing for scraped again, is made. You take the original book, which you find with the parchment. You use an acid made out of lemon juice and try to wipe it out as perfect as you can. Then you cut the 2 pages apart, turn them 90 degrees, and overwrite them with your own writings, rebind them, and you have your little prayer book palimpsest. It was this palimpsest which Johann Ludwig Heiberg had discovered in Constantinople in 1907. It did not only contain 7 of Archimedes' treatises. Two of them had been previously unknown. One of them, the method of mechanical theorems, the letter of Archimedes to his friend Eratosthenes. It also contained the only Greek version of Archimedes' famous treatise on floating bodies. Heiberg tried to get the manuscript out of Constantinople to Copenhagen, but they didn't let him do it. So all he could do is travel to Constantinople and, equipped with a magnifying glass, that was all the technical help he had at the day, he started to transcribe the manuscript. We know now that in his transcription of the method, there are significant gaps. After World War I, the Archimedes Palimpsest disappeared. In fact, Constantinople was looted to a large extent, and it was believed that it had gone forever. And then, I'm sorry, I'm going ahead. Let me say the importance or the significance of the method. And this is according to Reappearance, who is one of the leading scholars, a Stanford professor on Archimedes. And he knows the method very well. In fact, we work together with him. In the method, Archimedes combines pure mathematics with physical considerations. For example, by putting segments of geometrical objects on a balance, similar to what I just showed you at the law of the lever, he manages to measure the area and volume of geometrical objects. Basically, he's deriving geometrical discoveries by a physical thought experiment. The second extremely important point is Archimedes is able to perform infinite sums. He takes a sphere, for example, and calculates its volume as the infinite sum of circles from which it is made. This is a breakthrough comparable to the modern integral calculus. And most of you, if not in high school, you had to deal with that probably in college. Both findings are essential features of modern science, in fact, and it is no exaggeration to say that Archimedes' method was 2,000 years ahead of its time. Galileo, for example, was considered the first physicist who used mathematics to describe physical experiments. Newton is considered the person who invented calculus. And one can only speculate how people like Galileo, Newton, or Da Vinci would have developed if they would have known about the method from Archimedes. On October 29, 1998, shortly after the Archimedes Palimpsest resurfaced in Paris, it was auctioned at Christie's, New York, and sold to an unknown investor. Important to note here is that the person pledged not to limit access to an ancient manuscript. And the owner was contacted by Will Knoll from the Walters Art Museum shortly after the auction and agreed to lend the manuscript for an integrated effort of conservation and imaging. In fact, since 1998, there has been significant progress in understanding the method, because now, other than a magnifying glass, one could use modern technology, such as UV light or multispectral imaging, to better bring out the different texts. However, there was a problem. First of all, the palimpsest was in horrible conditions. In fact, since Heiberg had read it, until between Heiberg's 1907 and 1998, it was attacked by mold, and many of the pages have really deteriorated since then. Furthermore, curiously, 4 of the pages had medieval paintings on them. Heiberg never reported about medieval paintings. they could have been real, but it was suspected immediately that there's something wrong with that. And indeed, when looking at the manuscript Grecs de la Bibliothèque Nationale in France, published in 1929, you can see a drawing which is almost identical to the one which was found on the Archimedes Palimpsest. In fact, it had the identical size, which suggests very much that this was just copied from someone onto the parchment. We know now, in fact, only since about 2 months, that this painting was done after 1939 from the composition of the different colors in the painting. We do not know who did it, and we certainly do not know whether the person who did it knew what he was actually doing, whether he had any idea that there was text by Archimedes underneath. This is when I learned for the first time about the Archimedes Palimpsest. In fact, now comes Niels' introduction. I was at a photosynthesis meeting in Germany in November 2003, and I stayed home for one night with my parents, and my mother, as many mothers do, gave me a stack of journals and little snips of papers to read. And that's when I heard about the Archimedes Palimpsest. What struck me was the fact that the writings were done with an iron-based ink. I just had come from a conference where for 3 days we were talking about nothing else than spinach, and in that spinach, and now comes the question to you, what does spinach have in common with the Archimedes Palimpsest? We all know that spinach has a lot of iron. In fact, generations, or one generation, at least mine, had been forced to eat a lot of spinach because of a scientific error. At one point it was thought it has 10 times more than the other green leaves. It's not true. There's not that much iron in spinach, in fact. So don't worry about it if you don't eat it every day. Does it have more or less than the Archimedes Palimpsest? I was sure it has less than the Archimedes Palimpsest. In fact, the experiments we do on spinach show that this is really a trace element, and I could not believe that even the faintest text in the Archimedes Palimpsest wouldn't have some traces of spinach, of iron similar than to in our spinach. Now, what else do you need to look through matter, for example, through a painting? It's X-rays. And we all know that because we have gotten our chest X-rays done. And of course, the inventor of X-rays, and the invention just celebrated the 100th birthday, is Wilhelm Conrad Röntgen. And the first really X-ray image is supposedly that of his wife's hand, which also shows that the jewelry in that time was actually pretty big. Would you be able to image the Archimedes Palimpsest with such a device? And the answer is no, because this image is produced from a contrast. So what you do is you shine the X-rays through, and the part, in this case the bones, or this ring, absorb much more, and so it stays darker. If you have something extremely thin, or something of very dilute, extremely dilute, that contrast doesn't come out at all. It is like looking at the stars in bright daylight. The light of the stars is there, but we won't see it. Why? Because the sunlight is so much stronger. So what do? We look at the stars at night, of course. And that is very similar to the technique I'm going to describe you now. So please bear with me. We are now traveling to the inside of an atom, and I will show you here a schematic setup how an atom is built. It has a nucleus made out of protons and neutrons, and it has a whole array of electrons zipping around the nucleus. What determines an element is only given by the number of protons you have in the nucleus. If the nucleus has 26 protons, it is iron and nothing else. It doesn't matter how many neutrons it has. Those are different isotopes, but they're all iron. If it has another amount, like 6, it is carbon, etc., etc. Now, it also has the same amount of electrons to balance this positive charge. So iron has typically 26 electrons zipping around. Imagine now, as we know that the positive protons attract the negative electrons, imagine now you have a charge of 26 plus 26 putting a force on the inner electrons. You can believe that that is a very strong force, much stronger than, for example, a carbon nucleus, which has only 6 protons. And the way how the electrons experience such a strong force is that they are much tighter bound to the nucleus. In order now to remove one of those inner electrons, you need, for iron, a lot of energy, and for carbon, you need less energy. And in both cases, you need X-rays to do that. And I'm showing you now how it is done, and then I'm showing you as well what we are using for the imaging. An X-ray comes in, it knocks out the inner electron. That hole is immediately filled from the outer electron and sends out a second X-ray with a different color. Now, I use the word color in a larger sense because obviously X-rays do not have any color for our eyes. But the important point is that by looking at the color of the X-rays sent out, you can unambiguously determine what element you're looking at. Because that color strongly depends on how much energy you need to knock out the inner one, and then the energy difference between those two gives you that particular color. Let me show it to you one more time. This is another example. In this case, we're looking at this one, and it might be a closer shell. It falls in and sends out a different color. The imaging, the X-ray imaging of the Archimedes Palimpsest, of the iron in the Archimedes Palimpsest, relies exactly on that method. You look at a particular color of X-rays. How do you do it? First, you need the palimpsest, obviously. You need a detector and a very intense X-ray beam. And now, all you have to do is you move your palimpsest through the X-ray beam. Each time when you hit an atom or a series of atoms of iron, it'll send out a little fluorescence. You're done with one line, you go down and move to the next line. In that order, you basically scan your book back and forth and record each time when you get the signal, you record it in your detector, and you can make a map of an iron map in that case, or of any element you want of what you can see. Now, what you need for this is an extremely intense X-ray beam, as you can imagine. And you need a very small X-ray beam, because the size of your X-ray beam tells you how well you will be able to see the text later on. So let me finish. Where can you find such an X-ray beam? Well, we are at the Stanford Linear Accelerator Center, and there are powerful beams here. Of course, the most famous is our 2-mile-long LINAC, but we also have, if you go into this little corner here, not far from here, as a matter of fact, the Stanford Synchrotron Radiation Laboratory, which is an oval or almost round-shaped device which produces very intense X-rays. In fact, SSRL has been one of the first multi-user, multi-GeV, that is a very high energy lab of this kind. It started in the 1970s. Since then, there has been a revolution with these machines. There are now more than 50 operating around the world. at places like Harima, Japan. This is the largest one in the world. 1 mile circumference is so big, you will not find a 1 mile straight area in Japan. So what did they do? They built it around the hill. The Advanced Photon Source in Illinois, 1 kilometer circumference. Almost the sister lab, beautifully located below the mountains where the 1968 Olympic Games took place in Grenoble, the European Synchrotron Radiation Facility. Across the bay from us, with a beautiful view on the Golden Gate Bridge, the Advanced Light Source in Berkeley, and its sister lab, Bessie, Berlin. How does such a synchrotron radiation laboratory look on the inside? Basically what you do is you store an electron beam in a vacuum tube, which is surrounded by a series of magnets. When you force the electron, when you force the charge to go around, to be bent around, it'll send out this very intense X-rays. And you have, in principle, 2 or 3 different sources of X-rays. One of them is called bending magnet radiation. It comes out like a fan, similar to when you have your bicycle tire wet and you spin it fast, the water comes out like a fan, and it's annoying because your back gets always dirty. The other one are so-called wigglers or undulators, and they, in fact, force the electrons on a little slalom racetrack. And by doing that, you can actually collimate the X-ray beam coming out even further, and you get even more intense X-rays. X-rays from a synchrotron are between 1 million and 1 billion times brighter than the sun. And you can imagine, when I told that to the curator of the Walters Art Museum, I'm going to use a beam which is 1 billion times brighter than the sun to put it on your Archimedes Palimpsest. He was very happy. In fact, he of course didn't give me the palimpsest right away. We had to do several tests before. And I'll show you that in a second. This is the inside of a ring, just to impress you a little bit. These series of magnets, they are remarkable machines. And this are some snapshots on the experimental floor. These are where the users, like myself, use these X-rays. You see a control station here of a hard X-ray beam line. You see someone putting a sample into the X-ray beam. You see a complicated diffractometer device. And this is kind of an overview where you see that it's an amazing activity going on. Our lab, for example, has up to 2,000 users a year coming from around the world doing different research in our laboratory. I just told you they wouldn't give me the palimpsest. However, Abigail Quandt was kind enough to lend me, from her own private collection, a 19th century parchment, an English will, and you're welcome to come by after the talk and can feel how wonderful it is. This one is made out of sheepskin, very similar to the Archimedes Palimpsest. And the first test we did is we wanted to see, can we really image something? And I'm just holding it up right here. This is the word "or" from this text, and this is our X-ray iron image from that particular word. The resolution is something like of order 600 dpi. Some of you might be familiar with these terms. In order to protect the Archimedes Palimpsest from this very intense X-ray beam, we had to come up with a mechanism that each time when the beam was at the end of a line, we inserted a shutter to close the beam so that the palimpsest was not exposed to the beam. It would then move up to the next line, started to move, open the shutter again, and go back and forth. By doing that, we guaranteed that any given point of the palimpsest was no longer than about 10 to 20 milliseconds exposed to this intense beam. We also had a mechanism in case something fails, the shutter is just closed right away. In addition, we needed to come up with a air condition and humidifier system, because the conservator from the Art Museum, Abigail Quant, asked me to keep the document always at a 50% humidity level at about 70 degrees Fahrenheit. I got a lot of help from a student, Jessica Lee. She has now joined Stanford as a freshman, and we basically we modified a commercial humidifier for your house into one which requires the more stringent levels for the Archimedes Palimpsest. Let me now finally show you the palimpsest arrived in May, and here you see a page with a gold forgery. This is Abigail, she is basically was the only person who was allowed to handle these pages, and she is now inside our experimental hutch. We have taken this photo through the LED window. During exposure, during measurements, no one is allowed to be inside. There is an interlock system which keeps you out of that. What you see in the back is kind of a plastic tent. This was our very sophisticated construction for the humidification system. It was hidden underneath there, but it worked. I'll show you another view. Abigail has now left the hutch, and we are able to put the beam inside the hutch. Here, basically, you see a set of filters and slits. Those were these very fast pneumatic slits which could drop in at an instant in case there was a problem with the X-rays. And here, this is a different page now. You see a view of a little bit closer look. The X-rays came through here. There was a very tiny slit and created this X-ray beam, which is about 40 microns. That's just about the size of your hair, a little bit smaller than the size of your hair. And that's how small the X-ray beam was. And schematically, I show you again here how we basically then raster scanned this document back and forth. You can think of it as the world's most expensive copy machine if you want. Let me show you now our results. The first, I'll show you this corner, and this is the normal view you have, and it is really hard, if not impossible, to imagine if or that there is any text. And this is how the X-ray image looks like, and I'm blowing it up right now. This is what came out right off the computer. The horizontal writing is from Archimedes. The vertical writing is from the biblical writings. Both of them contain iron, so both of them show up. Also, unfortunately, in the drawing itself, some parts of the drawing also contain iron, and so these parts will be a little bit harder to read. In fact, we are thinking about ways where we look at different elements in order to read these parts. But certainly, these parts, you can start to find letters. For example, you can find a tau, you can find a theta, you can find maybe like a phi. If you're an expert of ancient Greek, it might help you. But you can imagine as well that it is not easy to read the text, partly because of the quality of the image, but also partly because of the fact that when the palimpsester tried to wipe out the old text, what he really did is he distributed the iron all over the place. That's what we do when we take an eraser and take out some of the things. So you can see actually there's iron all over the place. And it is not typically in a parchment that there's iron. This was distributed. Let me show you another image. This is now the X-ray image of folio 163. V stands for versa. It's the front side, and I'm showing you this. I'm showing you a part of it. Here you see again Archimedes text in the horizontal and the text above in the vertical. And I would like to point out a remarkable feature about the X-rays. again, you see some characters in this direction. These are Archimedes characters, and this is the prayer book text. The X-rays, for the X-rays, the parchment itself is actually transparent. But of course, if you have two texts on top of each other, the amount of iron adds up. You have the iron from the top layer, and you have the iron from the layer beneath. And you can see that here. You can see that at the parts where these characters overlap, you actually get more signal. So in our case, more signal means like a more white look of this. And this might help you to actually read underneath text which is above, because you can still see it. With an optical imaging, if something is above, it completely blocks it out and you will never be able to read it. So that can be very helpful. There is one difficulty with using X-rays. Because the parchment is transparent, you will see actually both sides. So it would be like looking, for example, at this page, which is written on both sides, looking against a light, and you will see the writing from both sides. So you have to somehow try to find a way to disentangle the front side from the back side. And in fact, by using images from both sides, so what we did is we imaged from that side and then turn around, image from that side, and then through a smart trick of one of our collaborators, you can then take these data and crunch them, as we say, and you will get out the front and the back side with different colors. And here I just show you an example of that. The front side writings would be in red, and the back side would be in cyan. Now, I would say you can take on your glasses. And I have to take mine as well, actually. Okay, please remember the blue goes to the right eye. That's the most important thing. Otherwise, you see six-dimensional. One of our colleagues, Bob Morton, he had the idea, why don't we do some stereographic imaging? And we did that. All you have to do is you come in through two different angles, just about the same angles as your two eyes are, and then you can print them in two different colors. And here's what you see. This is now a 3D image of folio 163 with the text of Archimedes on it. The first thing which you observe is that the parchment is actually waved. And you can see that very clearly. I hope you can see that very clearly. Second of all, with this 3D effect, you can actually get an idea of which of the writings is on the front side and which of the writings is actually on the back side. And for example, here on that right corner, you see clearly that this text seems to be like it is floating above the text underneath. So this is clearly from the front side, and then this text is clear from the back side. And I'll show you another example. Now you are zooming in really to a size. That is kind of the size the scholars like to look at these characters at. They want to have them as big as their computer screen, basically. And again, you can get a very good idea about how the different layers of text are at different components. So this method, so you can take off your glasses again. This method of using the three-dimensional way of looking at it, or the as they call it, stereographic way, might help in some cases for the imaging. Let me now finish with the outlook. We have just started the Archimedes imaging, and the museum will come back in March with the other forgery pages. In particular, of a particular importance is page 2 of the introduction of the method. That is underneath a forgery, and we hope we can read as much as we can of that page. It is basically the continuation of the letter of Archimedes to his friend Eratosthenes. The palimpsester was a busy person. They did not only find Archimedes in this palimpsest. There is text by a possibly unknown author, and we don't even know yet which elements are in the ink. We know there is no iron in the ink, we hope we might be able to help. What I was told is it is enough to read something like 3 to 5 words of any book in the world, and using supercomputers you can then deduce whether that is a new text or whether that is an existing text. So if we would be able to read, let's say, one line of this unknown writer, we might be able to come to a new text. Hyperides was a contemporary of Plato, and he seems to be rather important for some of the scholars as well. Within the next 3 years at the latest, there will be hopefully a full translation made available to the public of the Archimedes Palimpsest with all the treatises, particularly the method and the other treatises as well. And the palimpsest will be again on display. And it's not completely decided yet exactly where it is, but there's a chance it will be at the Field Museum in Chicago. And by showing you a couple of impressions of my collaborators and myself at work, I would like to finish with a thought. What would Archimedes think if he would be seeing us here using a huge machine to try to find the last words and characters of some of his work? I think he would say something like that. You fools of the 21st century. I like the fact that you use these large, round, beautiful objects to study my work. But I wish you could have recovered my treatise on flying objects. That would have helped you probably a couple of centuries. Thank you very much.
So, Uwe, thank you very much for a fantastic talk. We have time for just a couple of questions. I don't know if Uwe, can you answer any questions?
Absolutely.
Yeah, let's try it. Anybody got any questions for Uwe?
Are there other texts that this will be useful in analyzing?
Yes. So the question is whether there are other texts. I believe there are many texts. Very many texts where this technique should be useful. In fact, in England, some similar work is actually going on some texts. And I'm not a scholar, but from what I heard from my colleagues, that there could be many texts where this could be very helpful.
How much time does it take to scan one page or section 2?
Right. So that's actually a very good question. And it is surprising how long it actually takes, because what you have to keep in mind is that if you have a page, let's say, of this size, and you can very easily calculate how many of those small 40-micron pixels actually corresponding to 600 dpi are on it, and it turns out to be something of order 10 million. And so you can then estimate how short you have to stay on each of them in order not to make the scanning take a year. And in our case, it took us about 30 hours for a half page. And that seems like a very long time, but you have to compare it to about several months for the scholars to read it then. So in that sense, actually, our time is not that long. There was another question.
Is there another element besides iron to look at, or is that the obvious choice?
Yes, there are other elements. There is, we know that there's, for example, also sulfur in the ink. There is potassium in the, not in the Archimedes ink, but in the ink of the prayer book. So the thought is, if you use basically like a subtraction method, you can image the potassium and the iron and then subtract out the other text. The problem really is that, as I showed in this example of how this X-ray fluorescence, how this X-ray glow works. If you go to lighter elements, like sulfur, the X-rays do not penetrate as much anymore. And it is very difficult to look at these lighter elements, but we are making an effort. In fact, what we would have to do is put the Archimedes Palimpsest inside a helium atmosphere, and we are currently thinking about how to do that. One could humidify it, for example, a little bit.
What were the waves on the page? How did that happen?
Oh, the waves, yeah. So the waves on the page, which I showed, was basically a cartoon picture of an X-ray photon, which we call a photon, a part of an X-ray beam coming in and hitting the atom and knocking out the electron, and then basically creating this secondary glow. Now you might say, how in the world is it possible to hit anything as small as an atom? And atoms are indeed extremely small. The good news is there are lots of them. And so basically, if you have lots of them, you will hit one. You will never be able to tell exactly which one, but you will hit one of them. So that was the actually.
What's the sensitivity of your sensor? What kind of noise levels do you have on?
Are you asking about what kinds of concentrations or
Detector and the kind of noise.
Oh, okay. Well, our detector is basically what we call, it's a single photon counting detector. So in other words, it really counts every event coming in, okay? And in order to get an image that you can really, that is useful, that you can see, you need several thousand probably. And so that gives you kind of the limit. If you get to lower numbers, it starts to get grainy. Very similar to a photographic exposure. When you go to when you take a photo when it's very dark, you get graininess, and that's just due to the fact that the signal gets lower. But the sensitivity, I would say, the way to characterize it would be as a function of kind of how much concentration or how dilute you can be, so I could give you more details on that. Other than that.
Is there any damage to the material at all? Can you take another scan?
Yes, that's an excellent question. In fact, we did. So what we did is we took this parchment, this British parchment, and we went put it in the beam, and we did different times of exposure. Okay, and then after that, I actually sent these different these parts which have different long exposure times to Ottawa, to the Conservatory Institute, and they looked at the fragility of the fibers in there. So they did a very stringent test, in fact, much better than you would see, for example, with a microscope. And we came up with a dose of 10 to the 10 per pixel. And if you go back to the number we used about 1/100th of that for our current imaging. So in principle, we would be allowed to scan another 100 times over that same area. And at some places, in fact, we might need to scan longer, because if the iron gets very dilute, as the previous question was, you need to stay on a little bit longer in order to get a good picture. It's like your exposure time in your camera, basically.
Do you have to match the energy of the photons with the sort of energy required by the electrons?
Right. Well, in order to knock out the photon, in order to knock out the electron, all you need to do is go above the threshold to knock it out. So in fact, what you do is you don't want to go too close to the edge, because then your detector might see a lot of those unwanted X-rays, which are just scattering and not doing a glow also. So what we did is we went to an energy which was about 30% higher than the energy of the fluorescence. And that gave us a nice clean signal from the iron. Maybe two more questions?
People hold pens differently, okay, at different angles. Does your technique allow you to discern, like a blaze angle, one that is a preferred reflection or vector for such a thing, so that you could distinguish between one set of writing and another?
Yes, in fact it does. And it's a very good point you bring up. When we inspected the iron image of the text, you could actually see from which angle the pen was pushed, because when you then try to wipe it out, there is always more iron left in that corner where it is pushed in. And in some cases, optical imaging or UV imaging also brings that out. But in other cases, with the X-ray image, it becomes extremely clear from which side the pen was held.
If I understood you correctly, the original papyrus must have been 600 years older than what you're looking at.
Yes. Unfortunately not. It's the original, well, obviously, we are looking at a 10th century document. So the original, it's actually 1,200 years older than the original writing. However, the scholars have a very good idea of how often it was copied. And it is believed that the Archimedes text was copied no more than about 5 times when it made it into the prayer book. So the fact that it's in ancient Greek and the fact that it is such a young copy in the sense of number of repetition makes it actually extremely valuable.
So Uwe is going to hang around. So those of you who have more questions, I'm sure he's very happy to answer those for you. If you want to look at the bits of parchment. That's our last lecture of the year. We start again a new series in 2006, bigger and better. I'd like to take the opportunity to wish you all very happy holidays. Our cafeteria is open if you want a drink after all of this. So once again, Uwe, thank you very much indeed.
The original, well, obviously, we are looking at a 10th century document. So the original, it's actually 1,200 years older than the original writing. However, the scholars have a very good idea of how often it was copied. And it is believed that the Archimedes text was copied no more than about 5 times when it made it into the prayer book. So the fact that it's in ancient Greek and the fact that it is such a young copy in the sense of number of repetition makes it actually extremely valuable.
So Uwe is going to hang around. So those of you who have more questions, I'm sure he's very happy to answer those for you. If you want to look at the bits of parchment. That's our last lecture of the year. We start again a new series in 2006, bigger and better. I'd like to take the opportunity to wish you all very happy holidays. Our cafeteria is open if you want a drink after all of this. So once again, Uwe, thank you very much indeed.